In this lecture, we're going to look at a fundamental property of linear time-invariant systems. Now, we've defined systems as maps or functions from one space of input signals to a space of output signals. So because it's a function, a system associates with every input signal a unique output signal. And that output signal is called the response to the input signal. This fundamental property that we're going to look at characterizes the nature of the responses of LTI systems to any input. It's actually a property that we've really already seen, but we're going to look into it in a little more detail. Recall what we called the zero state response when we were talking about systems modeled by linear differential equations with constant coefficients. In that case, in the Laplace domain, we ended up with the equation y of s equals h of s times f of s. That is, we had a term on the right-hand side that depended on the driving function, or what we're now calling the input, f. And then we had another term that depended exclusively on the initial conditions and not on the driving function. That other term was called the zero input response. So if we're looking at the zero state response, we forget about that term because we set all of the initial conditions equal to 0, which makes it disappear. And we're left with this equation, which we saw last time. This is which we saw in the previous part of the course. So this is the equation that describes the so-called zero state response of a system modeled by a differential equation with a linear differential equation with constant coefficients. And in fact, it describes the zero state response of any linear time-invariant system. So what does this mean? How can we interpret this equation? We see that it looks as though in the Laplace domain, it's pretty easy to compute the zero state response of a system. We just take the input, f of t, find its transform, and multiply that by this quantity h of s, which we got from the differential equation modeling the system. But what does this function h of s really represent? What is it? It's a function that we're going to call the transfer function, essentially because of this equation. It lets us go very easily from the transform of the input to the transform of the corresponding output. But what does it mean? How can we interpret it? What is its significance in some kind of systemic sense? Well, another thing that we saw just before the break was the transform of a unit impulse. So we know that if f of t is the unit impulse function, then this factor f of s on the right-hand side is simply equal to 1. So in that case, we see that y of s, the response to this unit impulse, is this transfer function h of s times 1. So in other words, it's simply h of s. So that means that h of s is the response of our system to an input in the form of a unit impulse. And for that reason, we call the inverse transform of this function, h of t, the impulse response. Of the system. So this function h of t must be the steady state response, the zero state response of our system to an input of the form of a unit impulse. Okay. So knowing that, how can we further interpret this equation, y of s equals h of s times f of s? Again, in general, y of s will be h of s times f of s for any input f of t that has a Laplace transform f of s. So again, what does this represent? We know that this h of s is the transfer function. That's what we're calling it. And we know that in fact it represents the Laplace transform of the response, of the zero state response to a unit impulse. In other words, the Laplace transform of the impulse response of our system. So what does it mean that in order to get the response to some other input, other than a unit impulse, whose transform, say, is f of s, we just have to multiply f of s by h of s, this transfer function, a Laplace transform of the unit impulse? Well, again, we're multiplying here in the Laplace domain, and when we looked at the properties of the Laplace transform, we saw that the time domain counterpart of this multiplication in the Laplace domain is the operation of convolution. So this means that in the time domain, the response of our LTI system is in fact the convolution of the input f with the impulse response h. And this, in fact, is a very fundamental property of LTI systems. If you want to think of things in terms of computation, what an LTI system does is it takes its input and it computes its convolution with this particular function h, which is the impulse response of the system. So it simply computes convolutions, if you like. That's one way to look at it. Now, we've arrived at this conclusion using the Laplace transform, but we can actually show more directly that this is true. And when I say more directly, I really mean directly from the properties of linearity and time invariance. So we're going to prove this result more directly, and again this result says in words that the response of an LTI system is the convolution of the input with the system's impulse response. Now, it's easier to do this in discrete time. So I'm going to sketch the argument in discrete time, and then I'll simply claim that it carries over to the continuous time case. In fact, I think it will be pretty clear that it does. So first of all, what do we mean by a unit impulse in discrete time? Let's suppose that the domain, the set in which t takes values, is just the integers. We have 0, 1, 2, 3, and so on. In that case, the unit impulse is simply the function that takes the value 1 when t is equal to 0, and otherwise takes the value 0. So this is much simpler than a continuous time unit impulse, which you have to try to imagine as an infinitely high but infinitely narrow spike with an integral equal to 1. In the discrete time case, we can simply take it to be this function, which is in fact a real function. So that's going to make things a little bit simpler to think about. Now, the first thing to note is that this discrete time impulse has the same kind of sifting property that we used as the formal definition of the continuous time unit impulse. So this also satisfies a property that we can think of as a sifting property. So let's state this. Let's choose a particular value of t. Let's call it t naught, say. Then what happens if we take our function f, any function f, and I'm going to use tau as a variable of summation. So let's consider values f of tau. Suppose we take f of tau. I'm going to use square brackets to emphasize that we're talking about discrete time functions here. That's what the square brackets indicate. Suppose we take f of tau, we multiply it by delta of, let's write it this way, tau minus t naught, and then we sum over all values of tau, integer values of tau, from minus infinity to infinity. What are we going to get when we do that? And this is just a discrete time analog of what we did with the continuous time impulse. Well, as we sum over all these values, we consider all possible values of tau, of course, all but one are going to give a value of 0, because this impulse is equal to 1 when its argument is 0, but otherwise the function is equal to 0. So we'll only get a non-zero value when tau is equal to t naught. If that is the case, this unit impulse will equal 1. So the term behind the summation will just equal f of tau, but again, this is the case where tau is equal to t naught, so this whole thing will be equal to t naught. Sorry, I should use square brackets here. So just as in the continuous time case, when we take this summation, which is analogous to the integral that we looked at in the continuous time case, multiplying f of tau by this unit impulse, delta of tau minus t naught, summing over all tau picks off, if you like, the value of f at the particular value tau equals t naught. So this is why we call it a sifting property, because of the way it picks off this particular value of the function. The value that it has when tau, or t, if you like, is equal to t naught. So this is a sifting property. But of course, this property holds for any value of t naught. So let's drop the subscript and rewrite this. Then for the same reason, we have f of t is equal to this sum from tau equals minus infinity to infinity of f of tau delta tau minus t naught. That's just the same equation. But here I'm thinking of, if we think of t as a variable, sorry, I shouldn't have a t naught in there. If we think of t as a variable, t, rather than the constant t naught, then you could interpret this equation as saying that function f of t is the same as the function represented on the right-hand side of the equal sign. In other words, you can think of f of t as an infinite sum of impulses, delta of tau minus t, each occurring when tau is equal to t, or when t is equal to tau. In fact, I'm going to write it a little bit differently. Delta is an even function, just as the continuous time impulse function is, so we can write this as delta of t minus tau. So what's delta of t minus tau? It's simply the unit impulse that we looked at before, but shifted along the t-axis by an amount tau. So what we're doing here is we're summing an infinite number of unit impulse functions, each shifted by a different amount tau. So for every tau we have a different impulse function that is 1 when t is equal to tau, but otherwise 0. And we're scaling that impulse function by f of tau. So if we take all of these shifted and scaled unit impulse functions and add them all together through this summation, we get the function f of t itself. So you can think of this as meaning we can decompose f into what's sometimes called an impulse train, a whole sequence of impulses, one for each value of tau occurring when t is equal to tau, and scaled by the amount f of tau. So if you like, this equation decomposes f into a sequence of impulses, suitably scaled and shifted. Now, this sum is just a big linear combination. So given that we are talking about linear systems, if we want to find the response of a linear system to this input f of t, according to this equation, it suffices to find the response of the system to each of these impulses. And then we can simply apply a linear combination of the same form, not to the impulses themselves, but to the respective responses to those impulses. That's just what the property of linearity tells us. If our input is a linear combination of inputs, of other inputs, then the response is simply the linear combination of the same form of the respective responses to those inputs. So let's suppose that the response of a given LTI system S to an impulse, say delta of t minus tau, is some function h. Now this h is going to depend both on t and on tau, so I'm going to give it two arguments. H is now a function of two integer variables, t and tau, because the input signal that we're talking about depends on both t and tau. In that case, by linearity, the response y of t of our LTI system S to f of t is going to be a linear combination of the same form as the one given above, except where we replace the impulses by these responses to the respective impulses. Okay. That's just by the principle of superposition. Okay. So that is something that we get from linearity. But what about this other property that we've assumed, namely time invariance? Well, what about it? We're interested in the responses to a unit impulse and an infinite number of shifted versions of that unit impulse. Well, let's consider the ordinary unit impulse that occurs at time t equals 0. According to the notation that we've chosen above, the response of our LTI system to that unit impulse that occurs at time t equals 0 is h of t0. Okay. But then time invariance tells us that if we shift that impulse, say by an amount tau, we will get the same response, except that it too will be shifted in time. So we'll get h of t minus tau 0. But by definition, the response of our system to delta of t minus tau is h of t tau. So in fact, this function that we have written out as if it's a function of two variables, this h, we can in fact think of solely as a function of one variable, one argument if you like, because we've seen here that h of t tau really only depends on the difference between t and tau. We can make the first argument t minus tau and then always have the second argument equal to 0. That will give us the same thing. But if the second argument is always going to be equal to 0, then it doesn't really serve any purpose. So what we're going to do is just rewrite h of t tau as h of t minus tau. So we're going to consider h, in fact, just to have a single argument. Then we can rewrite our expression for y of t in terms of f and h of t tau. So y of t is going to be the sum as tau varies from minus infinity to infinity of f of tau times h of t minus tau. But this is precisely the convolution. This is a discrete time version of the two-sided convolution integral. So we can write it as f star h or as h star f. We know that by a change of variable, this convolution is in fact commutative. So we've shown directly from the properties of linearity and time invariance that the response of an LTI system to any input f is simply the convolution of that input signal f with the impulse response of the system. Note, for instance, that this notation that we adopted here tells us in particular that the response of the system to an impulse that occurs at time t equals 0 is now simply denoted h of t for our one argument version of the function h. So this h that appears in the convolution is simply the response of the system, a zero-state response of the system, if you like, to an input that arrives, an impulse rather, that arrives at t equals 0. And to find the response of the system to any other input signal, you simply have to convolve that input signal with that impulse response. So the response of an LTI system to an input function f, an input signal f, is the convolution of f with the system's impulse response. Okay, so that's exactly what we said on the basis of the properties of the Laplace transform, but now we've seen it more directly. We've proved this using only the properties of linearity and time invariance. And in fact, the analogous property holds for continuous time systems. So for CT systems, if our CT system, our continuous time system S, maps the input to the response Y, then Y of t is the convolution. And for now I'm going to write it as the two-sided convolution of F and H. Where H of t is the system's impulse response. So the same result carries over to CT systems, and in fact, just as in the case of discrete time systems, it follows from the sifting property of the unit impulse which you can reinterpret as saying that you can decompose F into a linear combination of impulses, and then when you apply to that linear combination of impulses the properties of linearity and time invariance, an analogous argument applies. I should specify that this is for LTI, continuous time systems. So this is that fundamental property of LTI systems that we set out to discuss and establish in this lecture. We won't be applying it very directly in the sense that we won't actually be computing convolutions. Obviously, it's much easier to multiply transforms in the Laplace domain. But this is a very important conceptual result to keep in mind. And that concludes this lecture.